Good morning everyone. I am here to record a lecture on Introduction to Semiconductors Physics, and this is the third lecture on electronic devices. So in this lecture what we are going to deal with, we are seeing about Schrodinger wave equation, wave duality particle, and what are the different applications of Schrodinger wave equations. So coming to wave particle duality principle, what wave particle duality gives? It gives a relationship between wavelength and momentum. So as we know, momentum is P is equivalent to m into V. We can write here that P is equivalent to m into V. So P is equivalent to m into V, and from here the momentum P is equivalent to h by lambda. So here the lambda is called as de Broglie wavelength. So this de Broglie wavelength will give you the information of how the wave is traveling inside the crystal lattice and the particle motion as a wave. So this wave duality particle principle is the third principle, as we have discussed already in the last classes about the Planck's relation, the Einstein theory, which is Eg is equivalent to h nu, and the Planck's theory, which is Eg equivalent to h nu for the particle motion, and the Einstein theory, which is for the particle photon as a particle behaving as a light. So wave particle duality principle is P is equivalent to h by lambda, where lambda is equivalent to you can write lambda is equivalent to P h by P, where h is the Planck's constant and its value h is 6.626 into 10 to the power minus 34 joule seconds. So coming to next part, that we have the electromagnetic spectrum. We have a very wide range of a spectrum, electromagnetic spectrum. It is defined as a range of the frequencies in which the electromagnetic radiations can travel from one place to another in different applications. If we want to use as a laser or LED, we have to use the radio wave frequencies, and if we want to use as a visible range, then we can use in the visible spectrum. So here you can see from the figure that the first one is the gamma rays, the second one is the X-rays. The gamma rays from 10 to the power 24 to 10 to the power 20, and in wavelength form it is 10 to the power minus 16 to 10 to the power minus 12. The X-rays, which has a range of around 10 to the power minus 10 micrometer. The UV rays, which is ultraviolet rays, is in the range of around 10 to the power minus 8. The infrared rays is around 10 to the power minus 6 to 10 to the power minus 4. The microwave range, which has a basic, we have already discussed that the gun diode, which is made of gallium arsenide, and it is in the range of the 10 to the power minus 2, which has a microwave applications. The FM range, that is 10 to the power 0, then the AM range, which are basically the FM and the AM are the radio waves, and these are from 10 to the power 0 to 10 to the power 2. And after that it comes to be long radio waves, which is 10 to the power 4 to 10 to the power 6 to 10 to the power 8. So it is from 10 to the power 4 to 10 to the power 8 micrometer. So which is the long radio waves. So this is the electromagnetic spectrum, and according to spectrum we can use these spectrum in various applications. As I have told you that for LEDs and for lasers we have to use the infrared rays, and for the visible spectrum we have the Vibgyor type of region. So this is all about the electromagnetic spectrum. So next is the principle which is the basic principle for the electron or the atom existing in the particular lattice. So this is called as Heisenberg uncertainty principle, and this principle states that it is impossible to identify uncertainty in position and momentum simultaneously. We cannot identify the position and the momentum simultaneously. That means that the position, that is delta x, and the momentum, that is delta p, is greater than equivalent to h cross. So we cannot find out the position and the momentum at a particular simultaneously at a particular time. The second principle of this Heisenberg uncertainty principle, it states that it is impossible to identify energy and time simultaneously. We cannot identify delta E and delta T simultaneously at the same time. So it is around delta E multiplied by delta T is greater than is equivalent to H, where H cross is equivalent to H by 2 pi. We can also write like this, delta X multiplied by delta P is equivalent to H by 2 pi or greater than equivalent to H by 2 pi. Similarly, delta E multiplied by delta T is greater than equivalent to H by 2 pi. So, these two relations will give you the uncertainty in the position, in the momentum and in the energy and the time. So, Heisenberg is a very well known scientist. Werner Heisenberg gives this principle, that is delta E into delta T is equivalent to H by 4 pi and delta X into delta P is equivalent to H by 4 pi, where delta E is the uncertainty in energy, delta T is uncertainty in time, H is the Planck's constant. Similarly, delta X is the uncertainty in position, delta P is the uncertainty in momentum and H is the Planck's constant. So, due to the energy that must be applied to a system to observe its certain pairs of variables like energy, time, position and momentum cannot be observed simultaneously, and it also includes the Pauli's exclusion principle, that no two electrons can be at the same time at the same energy level. The electrons must have to be at different energy levels in the same time. So, this is called Heisenberg uncertainty principle. We also have, for instance, position and momentum of a quantum particle cannot both be measured because of a high frequency photon used to measure the position precisely will give a poor momentum here, and vice versa for a low frequency photon. So, an intermediate frequency photon would only give micro readings here. So, uncertainty principle will give you the exact position or the momentum of the particle in a particular lattice structure. So, as we have already discussed in the last classes about the lattices, that the different type of lattices are cubic lattice, the body centered lattice and the face centered lattice. So, if we have a particular type of lattice structure and we have to find out the position of the momentum of the electron in that particular lattice, or the atom momentum or the position in particular lattice, we have to apply the uncertainty principle. We must have the uncertainty principle there. So, next, what is Schrodinger wave equation? So, this is a very important equation in electronic devices or in semiconductor physics. We already have discussed about different type of principles like uncertainty principle, Planck's constant, Einstein theory, but these theories will be you can say avoidable if you know about the Schrodinger wave equations. So, what is Schrodinger wave equation? Schrodinger has given that if the particle has a wave type of nature or the wave has a particle type of nature, the same way the vice versa, the particle must have a wave type of nature. So, this is the equation which describes the mechanics of a particle wave traveling from one medium to another medium. These equations give the mathematical representation of the electromagnetic wave whose properties are studied in all respect. We know that there are four kinds of Maxwell equation, that is del cross E is equivalent to deba B by deba T, del cross H is equivalent to deba D by deba T, del dot E is equivalent to 0 and del dot B is equivalent to 0. So, these type of four Maxwell equation which consist of for the electric field, for the magnetic field, for the free space and for no poles there. With these equations we can find out the plane wave equation easily. And with the help of the plane wave equation, which is psi is equivalent to psi naught exponential kx minus omega t, we can easily find out the Schrodinger wave equation. So, this equation gives a mathematical representation of the electromagnetic waves whose properties are studied in all respects. So, the wave function here is described with psi x comma t. So, psi is the wave function which is the function of the position and the time. So, the wave function describes the properties of the wave with respect to time, potential, frequency and the mass. So, the Schrodinger has given this equation in the form of this. The first form is minus h cross square upon 2m del square plus v psi is equivalent to I h cross deba psi by deba t. Here the first one is the del operator. So the del square is dy square upon dy x square plus dy square upon dy y square plus dy square upon dy z square, which is called as the Laplacian in Cartesian coordinate. So del square is the Laplacian operator, del is the Laplacian operator, and if we find out del square, it is same as del square upon dy x square plus del square upon dy y square plus del square upon dy z square. Here psi, as I have told you, psi is the wave function, because for the particle to behave as a wave, we have to recognize that particle has some function. So psi is defined as the wave function. Psi is the wave function, and V is the potential, and h cross we have already discussed, that is Planck's constant, which is h by 2 pi. The particle mass is represented by m. So small m is the mass of the particle, h cross is the Planck's constant, which is h by 2 pi. Del square is the Laplacian operator, V is the potential function, psi is the wave function, and with this expression the Schrodinger has given that it has both the position and the time dependency. The Schrodinger has given about the mechanics of the particle, that the motion of the particle as a wave. We have the wave nature for the light also. We have the wave nature for the different type of forms of the light, but for the Schrodinger wave equation we have the same thing, like the particle has a wave nature, the wave has the same as the particle nature. So the wave behave as a particle, the wave behaves as a ray, and the same way the particle behave as a wave. So the next is the first case of Schrodinger wave equation. So this is the first case. Schrodinger has given two type of equation. The first one is the time dependent and the second one is the time independent equation. So in the time dependent case of Schrodinger equation, which describes the wave function as a function of time only, not the function of the position, it is independent of the position. So this equation describes the relation of wave function with potential, mass and time only, not function. So this equation is mathematically representation of the wave function with time dependency. So if we solve the Schrodinger wave equation and we put some assumption there to have the position not dependency, only there will be a time dependency, we will get this relation I h cross is deba by deba t psi r comma t, where r is the position or t is the time, but this position factor of the wave function depends only on the time function. So minus h cross square upon 2m, where m is the mass of the particle, del square, as we have already discussed that del square is the Laplacian operator, or del square is dy square upon dy x square plus dy square upon dy y square plus dy square upon dy z square. V r comma t is the potential function and psi r comma t again is the wave function. So this is the wave function. This V r comma t is the potential function. Del square is the Laplacian operator. M is the mass of the particle. Okay, and h cross is again h by 2 pi, which is Planck's constant divided by 2 pi. So this is the first case of Schrodinger wave equation, which gives only the time dependency. The second case of Schrodinger equation. So in the second case of Schrodinger equation, as I have told you that it has two types of Schrodinger equation, the time dependency and the position dependency. So the second case is the time independent case of Schrodinger equation, which describes the wave function is independent of the time factor. Now the wave function depends only on the position. So this equation describes the relation of a wave function with energy, potential and mass, not on the time. So this equation is mathematically representation of the wave function with time dependency. So the second equation is time independent equation and it is equivalent to dy square psi upon dy x square plus 2m naught upon h cut square e minus u or v psi is equivalent to 0. So if e is greater than u, then in that case k, here k is equivalent to under root 2m naught e minus u upon h cross multiplied by this whole factor, that is day by square psi upon day by x square plus k square psi is equivalent to 0. The solution of this equation is given by this. So we have the solution in the form of day by square psi upon day by x square plus k square psi is equivalent to 0. So here we can easily find out the value of the k in the form of the sin x and the cos x. So psi x is equivalent to a sin kx plus b cos kx, or we can write like a plus e to the power I kx plus a minus e to the power minus I kx. So this is written here in the form of the wave function. So here if first case if e is greater than u, the second case if u is greater than a. If u is greater than e, then in that case small a, which has the value of under root 2m naught u minus e upon h cross, and in that case we have a relationship for the solution like this, that is day by square psi upon day by x square minus a square psi is equivalent to 0. So there are various applications of the Schrodinger wave equation. This is the first application of Schrodinger wave equation, that is the electron motion in free space. Normally the electron is bounded in the lattice. It has some force like the internal forces and the external forces. But in the case of the Schrodinger wave equation, if we apply the Schrodinger wave equation in a particular lattice, the electron motion we have to consider as the free space. So where the motion of the charged particles is random and it is continuously varying in the free space. So this is the application in which the free electrons will travel from one end to another without any obstruction. Normally there are two type of forces. The first one is the external forces and the second one is the internal forces. So we have two types of forces, and F total is equivalent to F external plus F internal. So as we know, F total is equivalent to mass into acceleration. So we have the concept of effective mass here. So effective mass here we can represent F total is equivalent to m star A. So here m star is called as effective mass. This effective mass accounts for both. What both? It accounts for the external forces as well as it accounts for the internal forces. So when the motions of the electron is in the bounded state or is in the lattice. So this is the case when motion of electrons in lattice in bounded state. So when it is bounded state, it has two type of forces, external forces, internal forces, and total force is given by F external plus F internal, and F total is given by mass into acceleration, and we can represent this mass is mass asterisk, which is called as effective mass. So this effective mass accounts for both the external and the internal forces. But if we apply the Schrodinger wave equation, we must have to consider, or only we can apply the Schrodinger wave equation, you can say, in the case when there is free electrons or the motion of the electrons are free. So you can see that the solution of the Schrodinger wave equation, in free space we have no forces. So earlier I have discussed that there are forces when the electrons are in the bounded state, but in the free space there are no forces, and the potential energy can be identified or described by VR is equivalent to 0. So if there are no forces, there will be no potential energy. For simplicity, we assume the first dimensional case, that is the first case, which is the time position dependent case. So this is minus h cross square upon 2m day by square psi x upon day by x square, which is equivalent to E psi x, or we can write psi x is equivalent to C e to the power j kx. So this is the equation for the position dependent case, and because we are considering here that is VR, or the potential is 0. So when potential is 0, there will be only the position dependent case, and from here we can easily calculate the value of k, which is under root 2 me upon h cross. So here we can write the wave function as similarly in the same way, that is psi x comma t, that is C e to the power j kx e to the power minus j omega t, which is the same as the plane wave equation. This is same as psi is equivalent to psi naught e to the power j kx minus omega t. So this is the equation which has the same form as the plane wave equation. Okay, so this is a solution for the Schrodinger wave equation. We can easily relate this equation with a position dependent case, and with the help of the position dependent case we can find out the value of the k firstly, that is under root 2 me upon h cross. Then we can find out the value of the wave function, which is psi x comma t, but the value is only for the position, that is C e to the power j kx into e to the power minus j omega t, and which has the same form psi is equivalent to psi naught e to the power j kx minus omega t. The second case or the second application of the Schrodinger wave equation as a potential well. So it has another application as infinite potential well. In this application, the potential well is limited to boundary region. So we can see from the figure there are three regions. The first region is this, the second region is this, and the third region is this. So we have three regions from 0 to A. Behind 0 there is first region, from 0 to A there is second region, and the third region is this. So we have the potential function as Vx is equivalent to infinity for x less than 0. In the second region we have Vx is equivalent to 0 from x is greater than 0 to less than A, and for Vx is equivalent to infinity for x greater than A. So this is the third region. So in this application the potential well is limited to boundary region, where the wave is analyzed from top to bottom. The number of cycles wave keep increasing from top to bottom, from bottom to top. The number of excited states also keep increasing from bottom to top. So we can see from the figure here that from bottom to top the number of wave functions will goes on increasing. Similarly in the first figure it goes on increasing. In the third figure we have E1, 4E1, 9E1. As the energies will increase, the excited state also increasing. So this is also increasing. So we have the relationship for the energy, that is psi nx is equivalent to under root 2 by L sin n pi x upon L, and the zero crossings are at sin n pi x by L, or we can write n pi x by L is equivalent to plus minus n pi. So we have the zero crossings according to the this formula. The energy is given by this, that is En is equivalent to h cross square upon 2m, that is multiplied by pi by L square upon multiplied by n square. So from 0 to L we have this wave function and this energy function. So next is the step potential case. So in this application the wave will enter from one medium to another, due to which the properties of the wave will change. So in the first diagram you can see that the psi x is in decaying for E less than V naught. For E less than V naught it is decaying, and for E greater than V naught it is increasing. So E less than V naught it is decaying, and for E greater than V naught it is increasing. So we have this type of relationship. In the second diagram the wave is entering into the other medium and it starts decaying by changing its properties. So it is from one medium to another, wave is going and it starts decaying from there. So this is the third application, is like the extended form of the potential well. So there are some potential barriers here. The wave is entering from one medium to another, which we have already discussed. So in the first region the incident and the reflected wave is present, having some specific constant. In the second region the wave enters into the medium where the properties changes with specific constant. In the third region what will happen? The wave exits outside the medium and again the property changes. So in the third region we see in the last case that the wave is decaying as the medium changes. So you can see from here from the figure also the incident wave, the reflective wave and the transmitted wave, and we have the relationship, same relationship, psi x is equivalent to a exponential ikx plus b exponential minus ikx. Similarly, for the region 2 we have psi x is equivalent to c exponential iqx plus d exponential I minus iqx. We have k already known, that is k is equivalent to under root 2 me upon h cross square. Here because of the medium we have k square is equivalent to 2 me upon eta square, and q square is equivalent to 2m upon eta square E minus V naught. So this is the electron in periodic lattice. Energy of the bound electron is quantized. We know only discrete value of electron energies are allowed. The wave function of two atoms will overlap. That is, the two electron will interact, which will result in discrete energy. So we can see from the diagram that we have discrete energy levels as the circles 2, 8, 18, 32. The first energy level is having the 2, then the 8 atoms, then 18 atoms, then the 32 atoms. So as we know that the electrons will reside in the discrete energy states, we have only the allowed energy levels for the electrons. No electron can be reside anywhere in the energy state. So there must be some discrete energy states. So I am stopping here. We will discuss about the electron in periodic lattice again in the next lecture, about how the discrete energy states are going to be formed and how the semiconductors are characterized in the form of direct and indirect band gap semiconductors, the variation in the form of the alloy composition and so on. Thank you so much.